my name is Nathan, as already has been mentioned, and I have a bit of bad news at first. This topic will be, oh wait, that wasn't supposed to happen, but that's okay. So my topic is on physics, and usually when I talk to people about physics, one of two reactions happen. Either they whisper to their neighbor, oh my goodness, this is about physics, it's going to be utterly incomprehensible. Or the other reaction is, oh, it won't just be incomprehensible, it'll be utterly boring. So, hopefully, we will all be able to participate in this thing in fiction which we call suspension of disbelief, which I encourage you to suspend your disbelief that physics can be exciting. Okay? So, I will be talking about scanning probe microscopes, and this is just really fancy jargon for something that's actually a very simple idea. But before we get into that, let me give you sort of an outline of how the talk will go. So if you enjoy the talk, or if you want to hear more about scanning probe microscopes, I have left a link to my PowerPoint, which has some annotated notes on it if you so desire. And this is how the flow of the talk will go. First, we'll talk about how do these microscopes work. How do they function, different from normal light microscopes that you've seen in the lab or whatever. Then we'll move into why this is important, what kind of scientists use this, what kinds of research is it used for, and finally, why is it important to me? Because in engaging in undergraduate research, I have learned a variety of lifelong lessons that I'll be able to keep with me, and some of those I wanted to share with y'all. So, let's first talk about how these things work. Now, scanning probe microscopy. Let's focus on the word microscopy for a second, microscopes, right? Most of you are familiar with traditional, light microscopes that you see in chemistry or biology labs in high school, right? You turn on a light, you put a microscope slide, and you can see cells and things like that. Now, the problem with those is that they rely on light. Light, as you may well know, is made up of waves, wavelengths, right? And these wavelengths can range from a few hundred nanometers long. Now, the problem is, I want to use microscopes to see atoms. And atoms are a fraction of a nanometer long. And so it is literally impossible to see atoms with the most powerful light microscope could ever build. So how then, if we have to throw light out, how else can we see? And if you saw my undergraduate research video, I talked about how we can learn a lesson from the blind community here, in that they don't use light to see. How do they see then? Well, a lot of the applications that have been made for the blind community is things like Braille, things like physical manifestations, right? If you pass your finger over a surface, you can feel the perturbations. And from there, you can kind of infer how the subject looks, right? And that's essentially what my microscopes do. I bring a super sharp probe really, really, really close to a surface, and the atoms between the probe and the surface begin repelling each other. So for example, the electrons begin repelling each other. Or just regular van der Waals atom-to-atom forces begin interacting with each other. And we can measure those things. And we scan these probes over a surface, and for every amount of distance, we take a measurement. And we make a pixel based on those measurements. And from that map of pixels, we can create a picture of the surface. And this is how we'll see atoms, and I'll show you a few pictures later. Now, there are two kinds of microscopes that I am specifically interested in, with fancy names that also are more fancy than they are actually. Scanning tunneling microscopy. Both of these are subsets of scanning probe microscopes. Scanning tunneling microscopes take advantage of this phenomena called electron tunneling. Now, what happens in electron tunneling is, electrons typically can't pass through things like insulators, right? Typically. Usually you want to use conducting materials to make a circuit. Well, there's this odd phenomena that if the insulating portion is small enough, the electrons will just magically jump across the insulating surface for some physical reason. And we take advantage of this by bringing, again, the conducting probe very, very close to the surface. We get an electrical response, and we can measure that. Atomic force microscopes use some of the forces that I described earlier, such as atomic forces between each other, repulsion, and also magnetic forces, which we'll be able to also see later. Now, this is research that can be applied in a variety of fields, and it has been applied in a variety of fields. These microscopes have been of interest for the past several decades. And a couple of fields, just to mention them, if you ever walk over to the nanotech facilities, or even some of the biology facilities, you'll see atomic force microscopes and scanning tunneling microscopes looking at small pieces of data, such as bacteria processes. You know, those electrical responses that you have between neurons, or microfilament forces, cell membrane forces. These things are measured using these microscopes. And obviously, nanomaterials, quantum computers, all these things can be made and analyzed with these kinds of microscopes. Now, this is all very theoretical right now. Let me show you a couple of pictures that we have taken. So this is a graphite sample that we measured, and these are actual graphite atoms. Now, remember, basically for each and every pixel, we scan the probe over to that specific point, we take a measurement of the repulsion between the probe and the surface, and then we move over and take another measurement, and from that we can build a picture. The bright spots you see are places where the forces are large. So that means the probe is extremely close to the sample, and from that we can infer that the sample is peaked at that area. And the same variety of the darkened spaces. Yes. So this is another sample that we had, and this is usually flat, and we can find really unique patterns through the magnetic forces.